Thank you. All right. Hello, everybody. Thanks for being here. I'm going to talk to you today about some ensemble data assimilation and estimating emissions. So Jin helpfully introduced 40 VAR to you all earlier, and so we're going to talk a little bit more about inferring emissions. So I'm Drew. I'm currently a postdoc at Duke, and I'm also starting as a faculty member at Oberlin, where I'll continue developing CHEEREIO. So I'm going to first talk about what ensemble data assimilation is, and then we're going to go through some technical details, and then show you what you can get out of this approach. So one thing that is very nice about the world today is that we have a lot of great satellite data, and this can help us monitor emissions. So we have these great satellites. They're observing the real world. And then in our geoschem land, we have our virtual world, and we can simulate what the world would be if all of our emissions were correct and the meteorology was correct and our chemistry was correct. And we can simulate what the satellite might see. And then we can compare it to what the satellite actually sees, and we find that they're not the same. And one reason why they may not be the same is emissions. Maybe your emissions are off. And this tool, CHEEREIO, is a way that allows you to fuse this information from bottom-up estimates with observations from satellites, but also surface instruments, aircraft, really anything you can get out of geoschem, and then makes a fused emissions product that's resolved in time and space, and with errors associated. So the way we put emissions into a model like geoschem is this bottom-up method, where you have some sort of emission factor. So you say that burning coal at this sort of power plant makes so much NOx per unit energy. You have a amount of electricity generated, and then you get your emissions from electricity, which you can map out based on where the power plants are. And then similarly, you can do this for transport, and then you sum this all up to get your total NOx emissions. And this is absolutely indispensable and a key part of modeling, because these inventories, they link these processes to concentrations, and that's really important for mechanistic understanding. But these inventories can take a while to make. They can have inaccuracies. And so observations can help us add to this approach. So the general method that I'm using in CHEEREIO is called the Localized Ensemble Transform Kalman Filter. And the original acronym for CHEEREIO was GCLETKF, but you can thank me that I came up with a much cuter acronym that is better than that. The basic idea is very simple. You have this source that's emitting some unknown, but you have an idea of what the emissions are. And you can say, oh, if we're emitting so much methane from this oil and gas area, the satellite should observe this much methane column concentrations. You can find that out with geoschem. Meanwhile, if you were to emit twice as much, maybe you'd observe a little bit higher column concentrations. And if you actually observe something in the middle, you think that maybe the emission source would be in the middle of these gases. Ensemble Kalman filtering is sort of a very grand Bayesian formalization of this sort of guessing and checking. So how does it look in practice? So what you do is you generate perturbations to your initial emissions map. The way this works in geoschem is you have scaling factor maps that go through HIMCO, and those perturb your base emissions. And so you perturb this. Red is making more emissions, blue is making less. Then you run geoschem for each of these maps for a day or a week or whatever period you're interested in. And this generates a bunch of different possible atmospheres, each reflecting these different emissions. And this emission perturbation is drawn from your overall uncertainty. So if you have a 50% uncertainty, you sort of perturb your emissions by about 50%, and you get the spread of atmospheres that result from your uncertainty. And you're taking a sample of this. So you're only doing this 16 or 32 times. So you're trying to sample the space of uncertainty. Then you simulate what an observer would see of these simulated atmospheres. So this is like applying a satellite averaging kernel or something like this. And then you use this to do a bunch of math. This is all abstracted away from you, the user, but I'm happy to talk about it if you want. But you do this Bayesian cost function optimization. Jin actually was very helpful in showing that cost function optimization. You're solving the same cost function in 40VAR or any of these data assimilation, the analytical inversion for all the methane and carbon cycle stuff coming later this week. It's all solving the same cost function. It's just doing the mechanistic work differently. So you do all this ensemble stuff to get all the matrices to do that math. And that gives you a new map of emissions. And then you just repeat this cycle over and over again. This gives you a time-resolved emissions maps evolving in time. So the way CHEEREIO works is it takes all this math and abstracts it behind a Python interface. So when you modify CHEEREIO, you're just modifying Python code, and you just put GeoSChem, a copy of the latest GeoSChem or whatever version you want, or your own custom version of GeoSChem in there, and then the Python interfaces with all the Fortran. You don't have to touch Fortran. So the idea is that with this one with this one configuration file, you modify it and you decide what your optimization problem is. So you want to optimize NOx emissions in this case, and you specify how uncertain you are, and then you can pick your model version and your inputs. So all of this is pretty standard GeoSChem. If you have your own fancy version of GeoSChem that you've been modifying to add a new mechanism or something, you can use that, no problem. It's just the forward model. Then you basically tell CHEEREIO where to find observations on the disk, and you can draw from the Python library online of people from different groups have contributed observation operators that can load in Tropomi, Yasi, other things, surface data, and that'll map onto GeoSChem. You can also add your own, which I'll talk about in a second. And then this all feeds into CHEEREIO. So CHEEREIO just makes this one big run script for you with all this input data. So I'll just pause here for a second and say, what are the various, there's a lot of ways of solving for emissions given, satellite observations or something like this. Ensemble data assimilation is relatively expensive, but uses only the forward model of GeoSChem, the GC Classic. So the cost is you run about 16 to 32 GeoSChem runs in parallel, plus you have this matrix multiplication weight, which does add to your runtime. So this is a substantial computational cost. However, it comes with the benefit of you don't have to modify any model code, and you use the latest version of GeoSChem. Alternative, the LETKF, if you do a bunch of math, you can squint, and LETKF and 40var are equivalent formally under some assumptions. In practice, that's not true, but the math people say that they're equivalent. But 40var is cheaper computationally because you're only doing the adjoint plus the forward model. However, you're then in the adjoint code base, which is great, but it has its own lineage. It's its own version of GeoSChem. So if you want to add in a bunch of new VOC chemistry, for example, I don't know what the status of that is in the adjoint, but you have a different code base. So depending on your problem, that might be a lot of work, or it may already be in there. The other thing is that this is in Python, which if you're scared of Fortran like I am, it's nice. So here's some cool results from CHEEREIO. CHEEREIO is pretty new, so the original paper is 2023, so we use it to look at methane. I think of this as the Pepsi to the integrated methane inversions Coca-Cola. So if you want some off-brand methane estimation, you can use CHEEREIO. So people are using it. It is cheaper than the IMI because 30 runs of GeoSChem is one thing, but 1,000 runs of GeoSChem is another. So I've learned after you leave Danielle Jacobs' group, you have a lot less money, and so it's actually kind of nice to not run GeoSChem 1,000 times. This is a pretty cool paper. So it does work global or nested. So you can do the nested grid implementation of GC Classic. So this is a great paper that's in review right now, run by Yifan Li and Bo Jiang's group at Tsinghua Shenzhen. So this is looking at what drives China's methane emissions and what drives trends. And she finds this really interesting result that livestock are driving it, even as China's coal phase-out policy has been successful. Dylan Jones's group has done some cool work with CO, and even was able to do some live assimilation in 2023 as the 2023 wildfires were going on, get some CO emissions in near real time. They got TCON into CHEEREIO, so that's neat. Some hot off the presses stuff, there's some CO2 inversions. This is more CHEEREIO Pepsi to the integrated carbon inversions Coca-Cola, but if you want to do your carbon there, that you can. I'll show some ammonia stuff tomorrow. And then Dylan Malay's group is doing some cool CRIS stuff, which will one day work. So here's how it works. So we have a big documentation. You can read it. It's extremely long, but I'll just give you a top of the line summary. So how hard is it to run CHEEREIO? So it's basically just GeoSChem plus some Python wrappers. So if you can run GeoSChem, you can run CHEEREIO. The challenge is you're running like 16 at the same time. So if that's feasible, you can do that. So it just requires GeoSChem inputs plus your observational data that you want to assimilate. The one nice thing is that this ensemble stuff is it's called embarrassingly parallel in computer science. It's not, I did not make it up. Stupidly parallel is another word that you might use. It's so dumb the way the parallelization works in the algorithm that you don't use MPI or OpenMP or anything. You can actually like list all the partitions if your compute cluster has different partitions, and you can submit all your GeoSChem runs to all the partitions and just flood your high performance computing system, which is what I do, which is when I get letters from the Duke computing cluster people. But you can do this. You do not need to share memory, so you can be completely across partitions. So the way you install, you go to Git, you clone it. It's mostly Python and Shell, and then you install GeoSChem inside it. And by install, I mean you copy your GC Classic code directory and just put it inside. So whatever version you have, as long as it's 13 or later, you're good to go. So the software environments, so whatever environment you're using for GeoSChem Classic, plus you need a Python managed by Anaconda or Mamba that needs to be in your bash RC. You need JQ, which is probably in your thing. That's just a lightweight library, and then parallel. These are very standard things, so there should not be any conflicts. If you have GeoSChem running, this is all you need. So you just modify your environment file or your bash RC to load all of these things. And then you also will need to install the conda environments that ship with this because it's all custom Python stuff. This is pretty straightforward if you're familiar with running GeoSChem and if you've touched Python before. But there's guides online if this is new to you. So this takes you to the part of actually defining the science problem. So this ensemble config.json file, this is how you entirely define the data assimilation problem. So what emissions are you trying to solve, using what observations, using what uncertainties, and then editing this file and getting it to be right is going to be the vast majority of the time spent in one of these data assimilation things. There is an extremely long guide to this file with a detailed description of every single setting in there online on this guide to the configuration file. I think it's like 50 PDF pages. So you don't need to like read it in advance, but definitely like search it if you think something's weird. You can also, we give you templates. So if you're doing something long-lived, look at methane. If you're doing something short-lived, look at ammonia or the NOx files and then sort of modify from there. That's a good start. You can also just email me and I can give you whatever versions I'm using recently. At the top of the file is basically your GeoSChem setup stuff. So it replaces the GeoSChem run directory like installation thing where you pick your options. So you just put those in at the top. And then this is where you start getting into your ensemble configuration. So ensemble data assimilation is its own universe with its own logic. And so you need to go into ensemble mode when you start thinking about this. So we have our own version of spinup in ensemble land called ensemble spinup. And the way this works is you have one restart file that is the one that you're interested in for your simulation. You have spun it up the way you would for any other GeoSChem run. But you need to have a spread across all your ensemble members because the spread is what defines your covariance matrix. That spread across your simulated atmospheres is representing your uncertainty. So you need to run GeoSChem for long enough that the different emissions fields in the different simulations, all these different ensemble members, are that emissions have time to propagate to concentrations. And there are some built-in cheat codes, like Lee was saying, if you want to spin up faster, like by scaling something by a lot. But this is sort of how you define it. You simulate, and then you stop at a certain point, and then you start assimilating observations. And then once you start assimilating observations, your ensemble will move in that direction. So this is an area of your ensemble config that's very important to get right. But luckily, there's a lot of examples for you to look at. Then you define what you want to optimize. So you can optimize concentrations, emissions, both. I guess you could optimize neither, but that wouldn't do anything. So the way you do this is you fill in these inputs. So the important thing I'm going to leave out the state control vector distinction, but the important thing is that if you want to optimize concentrations, so that means that in addition to like doing these emission fields, you actually perturb the 3D concentrations to better match observations. This is a nice way of preventing attributing transport errors to emissions, because there's always going to be transport errors that you can just fill in there. So on the left, we're optimizing both ammonia concentrations and emissions. So I did this in my methane paper. This was helpful because it prevented some weird noise from happening in our data assimilation process. On the right, I'm showing a case where we're optimizing NOx, SO2, and ammonia emissions, but we're not touching the concentrations. So you can see that you can group species together. So NOx is NO plus NO2. You define it, but you can do anything. It doesn't need to be scientifically valid to be a valid configuration file, which is dangerous. So you need to make sure that you're thinking about it, that what you're optimizing makes sense. So here, that's how we've defined the problem. Then you tell CHEEREIO about how to load the observations you want to use. So here we're optimizing these 3 species, and then we're telling CHEEREIO that we're observing certain species. So the species you optimize are not necessarily the same as the species you observe. This is nice because you might want to do something crazy like observe PM 2.5 and then optimize ammonia emissions or something. You can do that sort of problem. That is perfectly valid, and you can think about what observations have useful information. Formaldehyde to optimize VOCs. All of these are valid ways of doing configuration. So here, this is from the same file. We're observing NO2, SO2, and ammonia from different instrument types, from Tropomi and from IASI. And then we tell CHEEREIO where to look for these files. And it's basically mapping these keys and values to look for things. The valid options for operators are in this separate file called operators. So this is all the existing supported ones, supporting observations, but you can add your own following a very detailed guide online, which I'll talk about in just a second. But the idea here is that these observation operators are the absolutely key part of any data assimilation problem. It tells you how to map these observation files onto GeoSChem. And it'll be a major source of consternation at our data assimilation and inverse modeling working group breakout meeting is what are we going to do with all of our observation operators? So here is how we tell CHEEREIO to load these observations. So we are observing these species. So in this configuration, we're using both methane from OBSPAC, from surface observations, and then methane from Tropomi. But what we've done is that we've decided that we're only going to assimilate Tropomi, and we're actually going to just keep OBSPAC as a separate validation data set. So we just want to compare our results to that online. And so we've turned on Tropomi for LATKF updates. So our brain, we're chugging Tropomi into our ensemble Kalman filter, but we're using OBSPAC as a validation set. You could also optimize them both. So if you want to do joint data assimilation, that's all valid. You just need to think about all your uncertainties in these configuration files. To actually deploy it, this is the same as the IMI. If people know the integrated methane inversion, it's basically these shell scripts where you set up different settings to install different files. It's basically making an ensemble of GeoSChem run files with a bunch of extra junk involved to coordinate them. So you just go into this and modify it. There's a detailed guide online, but it makes this ensemble run directory, which has these 5 folders in it. There's a template run directory, which allows you to make final custom modifications that you couldn't express in the ensemble configuration file. There's a post-processing file where CHEEREIO will dump all the beautiful images it's generating to automate your PhD. And then we have our ensemble run directory. So this is all of your GeoSChem run directory copies with their own separate tools to coordinate them. And then there's the Scratch directory, which you shouldn't look inside. You can look inside there, but it won't be helpful. So once you've done all that stuff to make these ensemble directories, you can go in and modify things and tinker with things to make sure everything's to your liking, because you can't really express everything in that JSON file if you want to set your history settings to something else. So you go in and modify that. You can go in and see if CHEEREIO linked all the emissions correctly. So in this case, we wanted to optimize all of the methane emissions. So it does this in HIMCO and the HIMCO config file by putting that 700 out there. That's the code for the scale factors. And then at the bottom, it links those scale factors to a netcdf file. So this is deep HIMCO, but this is the way CHEEREIO handles the connection between its optimization in GeoSChem. This is why it works with every version of GeoSChem, is because it does the link through HIMCO. So you just want to make sure this looks right. And if you don't want to, like for methane, I didn't want to optimize the soil sink, but CHEEREIO automatically put a 700 there, so you have to take that out. So you just want to look through everything. There's a bunch of warnings. It warns you, make sure that I did it right. And then finally, it will generate all of these ensemble members, and you're ready to go. And the way that looks, let me just skip ahead to what happened. Sorry. So the way it looks is you go into your ensemble, configure your ensemble directory, and then you just run your ensemble spinup. That's that run on spin. So that will run like regular GeoSChem for however long you set it to run. And then it'll all set up itself to run the actual ensemble and give you your results. I'm just going to really quickly talk about these observation operators. So the way CHEEREIO is designed is it's this nesting set of Python objects that go to more and more abstract levels, so that you as a user, when you're modifying, you never touch the actual ensemble Kalman filter math. I mean, unless you want to. You just touch like, how do you link the observations? So if you want to add a new observing system, you just touch that and everything else gets abstracted away and your operator plugs right in. So it's designed in this object-oriented way. So CHEEREIO provides you a template for observation operators. If you follow the rules of the template, then whatever you add will plug right into CHEEREIO and work perfectly. And the way it enforces the rules is called inheritance. So it will fail if you didn't follow the rules right. At least it should fail. And this is helpful because it saves you a lot of time if it doesn't run for like 3 weeks incorrectly. So this is an example of an observation operator. This is for OBSPAC. So this is like the surface data that comes with that NOAA puts out of like carbon gases. So this class inherits observation translator. That's the CHEEREIO like template that is telling it what to expect. And then there's a bunch of optional methods that speed things up. But the important thing is that this mandatory function, this get observations. So there are 2 mandatory functions that every observation operator implements. There's basically a function that loads the observations from file and puts them into this standard dictionary format. All this is to say that once you have the data in this standard format where you have longitude, latitude, altitude, all those mandatory variables in there, everything else in CHEEREIO works fine. It's going to look for these fields later in the code that you don't touch. The only mandatory ones are longitude, latitude, time, and then value, whatever the value is. Everything else might be used elsewhere, but they're not mandatory. So, and then there's a function called GC-compare. So how do you compare it to GeoSChem? OBSPAC's really easy because GeoSChem outputs things with the OBSPAC operator like on to map things. So you just load in whatever GeoSChem outputs. So this is like a trivial observation operator, but there are much more complicated ones where you're applying averaging kernels and sort of thing. So you just write this the way you would write any way to compare GeoSChem to an observation. And I'm happy to help. I'm going to skip that figure. This is how LATKF works. Well, the good thing is that it's all abstracted away, so you never have to worry about it. So as your model is running, you can run a snapshot.sh. So this is a shell script that does a bunch of Python. It's very fast. So you go into the post-processing folder and you just run snapshot.sh. You can run it in Gossip Girl mode. That is a special CHEEREIO mode where it gives you all your output statistics with commentary from the Gossip Girl characters. I don't know if that appeals to anyone, but you can do it. So it saves things out. It saves out all of these data files, these pickle files and netcdf files, so you can do your own custom workthroughs. But it also outputs some key diagnostic figures. So this is your observation minus forecast. This is very standard data assimilation figures. So on the left, it's showing you basically the control run, so GeoSChem no assimilation minus observations. And you can see that in this case, GeoSChem is biased low in methane. This is just the way it was set up. And then on the right is the post-data assimilation one, where we've scaled up methane emissions to better match observations. And you can see that it looks a lot better. And it puts them on the same color bar. In general, you want to see things getting more and more white when you go from left to right. It may not be equivalent everywhere, but you want to get to those colors nearer to 0. It'll also show you a global mean trend plot on the right, but this is dangerous if you're looking at a short-lived species like NOx. The global average NOx mixing ratio is not super meaningful. So you're going to want to look at that figure, like the overall trends, if you're looking at methane, as we are here. So you can see that our ensemble mean, our blue, is getting closer to green, our observations, and are going away from our control. So we're solving our bias problem. But again, be careful. In general, this figure, these observation minus forecast figures, are going to be what you want. It also updates your emissions scaling factors, but you can also look at the HIMCO output. So this is basically HIMCO applies the scaling factors to your emissions so you can get emissions in unit of emissions rather than in units of scaling factors. That's a very helpful data to look at. I'll just quickly talk about what the output units are. This is going to be in NetCDF eventually, but it's not right now. It outputs this big Y. That's because in the math terms of data assimilation, your output is this letter Y. So this is the way it looks. For every day that you do an assimilation, it'll look at every basically observer that you have. So in this case, we're looking at methane from Tropomi. It'll give you the geoschem outputs for every ensemble member, compare it to the observations at a particular latitude and longitude, and then also have the control geoschem with no data assimilation. So this is the raw output and allows you to make your maps and your time series. So this is an example of what it looks like. You can see that for these different timestamps, we have these different methane mixing ratios. The ensemble members do not agree with each other because they have different emissions. It also automatically grids it for you, this big Y arrays for plotting. So you can automatically plot your simulated observations. So the geoschem ensemble mean with operator applied, your observations, everything else, and make these plots. So I'm at the end. So I'll end with a hopeful promise and a dire warning. The great thing about CHEEREIO is that you really do get your first results fast, especially if the observation operator is in there. Compared to like adding a bunch of Fortran to something, you can get a result fast. The dire warning is that the results are going to be catastrophically wrong. So the thing is that there's a lot of parameters. You saw them, it's a lot of parameters. And those parameters need to be tuned in match observations. There's a whole giant literature in data assimilation about how to pick assimilation windows. It has its own language. It has its own people. They're all physics people, and they're very mean at AGU, the data assimilation people. But luckily, there's a lot of example configuration files on the GitHub. I'm also happy to help. I've put some general guidance on the read the docs of problems that people run into where like you ignore observations or you overfit to observations and how you might address it. But generally the best thing to do is just dump all the CHEEREIO output into an email and send it to me because there's not that many ways it goes wrong. Also, there's not that many CHEEREIO users. So far this is sustainable and I am happy to help you. But if you all start using CHEEREIO, maybe we'll have to think of something else. But right now, this is a good option. I'll also refer you to whatever papers. But yeah, that's CHEEREIO. So I'll just leave this up here. There's a website, cheery.io. I thought it was a great domain name. Yeah. Anyway, so that's it.